the module. So just a bit of announcement, assignment 1 due tomorrow in lecture if you have done it. Right, so here are some topics for this week. They get a bit more complex than things we've done before, so it's less of a revision, kind of. It will be some real new stuff here. And it uses some language we have to become familiar with, namely this Zn star business. Okay, so let's start somewhere. So I'll start with the theorem, which is this Euler's theorem. And it says the following. So if it's like Fermat's little theorem, but now for arbitrary positive integer. So if n is an integer and a and n are coprime, then there's a certain statement about how to make 1 as a power of a. So I have a, which is coprime to n, and I'd like to see which powers of a are 1. So first of all, it happens that some powers are 1, and second of all, here is the power we need to take. So recall, so here it connects to what we did last week. This is Euler's function. We spent some time computing values of this and showing multiplicativity. Okay, so some remarks. Remarks. So first of all, let's just see something familiar in here. So if n is a prime, so would anyone like to tell me what is phi of p? Anyone with me here? So I hope some people, yes, please.
P minus 1.
Yeah, thank you. Thank you very much. So these kind of things we should be familiar at the moment, otherwise it's all lost basically, right? So if we have no idea what's going on, it will be a bit difficult for you. Okay, right. So in this case, you see the theorem is telling us, so Euler's theorem is a to p minus 1 is 1 mod p if GCD is 1. So in this case, Euler is Fermat. Yeah, that's exactly the same statement. And in the same kind of direction, if one assumes Fermat, so one can prove Euler's theorem using the following ingredients. So kind of Fermat's little theorem, induction on the number of primes on, you see, in general my n will be, so this connects also to last week, so typically it's convenient to factor out n like this, and maybe there will be induction on the number of different prime factors, and also Chinese remainder theorem. So this will be a bit like RSA business, so I know something modulo various primes, and putting them together will be Chinese remainder theorem. So one can give a little bit of a long proof using this thing. So this will be a base of induction, then somehow we get kth power, and then we put them all together. But this is not how we'll prove it. So we'll prove this theorem using group theory. It will be a one-line proof. It will be very simple proof. Okay, and also let's do an example of this. That's always fun. Example. So I should take something which is not prime to make it more interesting. So let's take n equals 10. So if I want to do phi of 10, which is relevant here, I should do phi of 2 times phi of 5. Now it's p minus 1 as we agreed, so it's 1 times 4. So this is 4. In other words, it's a number of integers up to 10 coprime to 10, which are like 1, 3, 7, and 9. Okay, so now, right. Now I need to think of this condition. So I want an integer, positive integer, let's say such that it's coprime to 10. So these are these guys. So 1, 3, 5, and 7. And the statement is that whenever I take any one of these into this power, I get a 1 mod 10. Yep. So Euler's theorem is that a to the 4th is 1 mod 10 for each of those a's. So in principle I can add 10, so multiples of 10, but I just have to check this if it's more 10. Okay, so there's not much to check, so it's okay, 1 to the 4th. Now 3 to the 4th. So we have some cool techniques, right? So 3 squared, squared. Okay, in any case it's 81, which is 1 mod 10. And similarly for the other, okay, let's see. Sorry. So you see, this is kind of the problem that everyone sees a mistake and no one tells me. So yeah, okay. I didn't mean this, of course. I meant the coprime one. So 7 and 9. Yeah. I would never be able to get 1 as a power if my number is 5, because it always will be divisible by 5. So I need to look at the ones which are coprime to 10. Okay, but now the other two just follow because I have, for example, this is the same thing we've seen before. So this is, we already checked this. So it's 1 here. Minus sign is gone. And the same for 9, which is minus 1. Yeah, so 4 things, all 1. And you see, of course, it wouldn't work. So n minus 1 is 9. If we try to do Fermat little theorem kind of thing, it wouldn't work. 9 is not the power which would make a 1 here. And 4 is. Okay, so basically, I said we give a one-line proof, but it will require some techniques. So we need to recall some bits of group theory. So we'll need really simple bits, but we'll use them over and over again. So in the notes I give a bit of an extended overview. Here I'll give a brief one. So I'll just recall definition of a group, and maybe a subgroup, and then an order, and then we'll apply it here. Okay, so we have set with an operation, binary operation, which means that it's 2 elements from G and spits out another element from G, and then is a group. So there are these 3 axioms you should know, and I should know. Let's see. So they are called associativity, neutral element, and inverses. So this means that A star B star C is A star B star C. So it doesn't matter which way I open up the brackets. Neutral element means that there exists an element from G such that if I times on either side with this, I get the same element for every G. So there exists neutral element such that this holds for every G. And inverses means that for every for every G inside G, there is an H inside G such that GH is HG is E. In this case, we write H to be G inverse. Sorry. Okay, so some more definitions. So G is abelian if G star H is H star G for all elements inside group. And also G is finite if it is finite as a set. And in this case, I write modulus G for number of elements. Okay, so this is what we need for now, so let's think of some examples. So, examples. So Z with plus is a group adding integers make them a group. The inverse is minus. Okay, so another one is this Zn with a plus is a group. So actually also we can say this is a billion and this is finite and the billion. So here this is this business about if I have Z5, my elements are 0, 1, 2, 3, 4, and the operation is 2 plus 4 is 1 kind of thing. Yeah. Additive group. But also what will be the most relevant for us is, okay, so let's make a statement. So the Zn star, which let me remind you are elements mod n such that they are coprime to n, is a finite abelian group Okay, so this was additive, but now I mean with respect to multiplicative operation. So I want to multiply elements, this is my operation, so with respect to multiplication. Okay, and also I can say of order phi of n. This is the, okay, yeah, sorry, this is called the order of the group. Order of the number of elements is called the order. Okay, so let's read again. So they have this Zn star, which I briefly introduced previously. These are elements in Zn, which are coprime to n. I consider operation multiplication, and I said it's a finite abelian group of order phi of n. So if we know what we're talking about, there's not much to check here. So let's just think a little bit. So, right. So I'm looking at this, Zn star with respect to multiplication. And so associativity is A dot B dot C is so we can just say that it's true since it holds for integers. So multiplication here is defined using normal multiplication of integers, and because this is something which is true for integers, it also will be true here. Neutral element. This is this one bar, so 1. And clearly 1 times a, 1 bar times a bar is the same as this, the same as. Again, we have 1 which is kind of 1 in integers. Yeah. So inverses, so I'm checking these axioms. Inverses, this is this business about solving linear congruences. So since since GCD AN is 1, A is invertible mod n. This is something we discussed before. Invertible mod n means inverse precisely this group under multiplication. So we restrict to this condition precisely to make this into a group. Okay, now abelian, this is obvious again because AB is BA since it's true for integers. So finite and order. So finite and order. So this is something we briefly touched upon last time. So you see, if I'm looking at the set of all those guys, that's the set of k bar from this in this list. So I can write from 1 up to n bar such that GCD is 1. So this is my order. But that's precisely what we call phi of n. So there are finitely many of those clearly because we look at finite list. And we call this number phi of n. That's the Euler function. So really not much is happening here. There's just kind of a language to package several things we already know. So Zn star. So we kind of checked that it's a group, abelian, finite of this order. Okay, just kind of to get a bit of a break from the general thing, so let's look at an example. So if I look at Z25 star, so we haven't seen this guy before, let's think a little bit about what is this group. So first of all, I know that the order is phi of 25. Sorry, so let's do something different. So 25 is a little bit too big for now. So let's take Z8 star. It still will be interesting, but more under control. So phi of 8, I need to take, according to one of the properties of the phi function, I need to take p to the k minus the previous power. This is my phi. So it's 8 minus 4, which is 4. And now it's easy to list those 4 elements because they're just odd elements. So 1, 3, 5, and 7. Yeah? And now you can imagine making a multiplication table for these guys, right? So kind of it will be a group under the operation where you take like 3 times 5 is 25, sorry, 15. And 15 mod 8 is a 7, and we can make the whole table multiplying these guys onto themselves and filling it out. So that's kind of what these are the things we're talking about here. This group under multiplication. And also we can think about inverses. And here, funnily, for example, 3 inverse is 3. Right, so if we take 3 times 3, we get 1. So this kind of stuff. So we need some more definitions now. So let G be a group, and G small be an element. And actually, let's assume G is a finite group, so finite is a set. So the definition is this, so the order of an element. We write order of G and we specify where we take it if it's not clear. Right, so that's the following thing. That's the minimum positive k such that G to the k is neutral element. So this should make us think about things like Fermat's little theorem and Euler's theorem. So we are taking powers of G and would like to end up with neutral element. So for example, right, so what would be a good example? So if I look at Z5 with respect to the addition, and I look at various elements, for example, 1. Right, so here it's additive group, so this neutral element is 0, and this taking powers is taking sums of elements with itself. Do people see what is the order of 1 in this group? So again, I hope, yeah? 1. So you see, 1 would mean that I take the first power, and it's... so you see, we need to translate this into additive notation. So I'm looking for k such that a, so k times a is actually 0. Right, because this is multiplicative. Yeah, there was a little bit of a trick here. So this is multiplicative notation, which will be relevant when we study this group of interest. But if it's an additive group, we're thinking about kind of making this 0. Anyone has a suggestion? Yeah?
4.
4, right. But if we take 4, it's kind of reasonable guess, but this is 4. So it's not quite 0 here, right? So maybe we can get a 5. So it's, you see, it's about adding elements. So we have 1, then 1 plus 1, still non-zero, still non-zero, still non-zero, still non-zero, and then this is 0. Yeah, so it's actually not quite 4, but 5, actually. If I take 5 once, I get 0. Yeah? Okay, and if, right, so it's kind of fun to play with this, but of course, not of course, but one can see that the other ones have order 5 too. And maybe also let's think what's the order of 0. It's a little bit of funny. So I want to get 0 as a multiple of 0. So how many, what's the smallest k I should look at? So 1 is the right thing, right? So kind of I just need to take one of them and it's ready. So, yeah? Okay, actually I think it's, yeah, okay, so let's also look at Z6 with a plus, even though it's not our main concern, but it's good. This is a bit simpler from what we'll be doing next. Next we'll be doing this kind of stuff. This is a bit more straightforward, so let's think a little bit about. So here it was a prime, here it's not a prime. Ooh. So let's think about order of 1, order of 2, and order of 3. So I like that people answer my question. So let's get more interaction. So do people see what is order of 1 in this group?
6.
Yeah, exactly. So this is the same as we did before. This will be a bit different. So we need, what is the order of 2? Yeah, 3 is good because we just take 2 plus 2 plus 2 and we get a 0. The point is that 2 is not coprime to 6, so it's easier to kind of make it 0. So what's the order of 3? 2. Yeah, exactly. So the order can be smaller than the order of the group. Yeah. So here we have the group of order 6, and sometimes the element has this order, sometimes has smaller order, and this will be important for us. And we can do the other ones, of course. So. Yeah. Okay, now let's do some multiplicative groups. So let's look at this group, Z8 star. So when it's a star, it always will be with respect to multiplication, as opposed to when it's just this, it will be with respect to addition. But this will be the more important one. Okay, so let's look at various orders. So order of 1, order of 2. Sorry, so the elements are here. 3, 5, and 7. So now everything is in terms of powers and in terms of 1 rather than sums and 0. Okay? So what is the order of 3, for example, in this group? It's already written here somewhere. What is the order of 3? So not quite. So let's see. We are solving the following equation. So we want 3 to the k is 1. for minimal positive k, right? So what is it now?
2.
Yeah, exactly. So this bit was the same as 3 squared being 1. 2. How about order of 5? So in practice we just start taking powers and see when we end up. Is it also 2?
3.
You see, if it's 2, 2 is better than 3. So 5 squared is 25. Mod 8 is 1. So it is actually also 2, right? Because squaring 5 leaves a 1. And how about 7? Yeah, 49. Yeah? So 1 mod 8. Okay, how about order of 1? That's always the same answer. Kind of. It's the same as this thing. So here everything is multiplicative. So the order of 1 is, order of the neutral element is 1. Because you don't have to take any powers. It's just the first power here. Okay. So let's get a different viewpoint on order. So that's the following observation. So if G is a finite group, and I take an element from this, then so I want to express order as something else. And the something else will be the number of, so the I look at various powers of G, positive and negative, and then I form a subgroup by taking this power. So I count how many elements there are. Yeah. So this is, you can write it like this. Subgroup generated by I take all powers, positive and negative, this forms a subgroup, and now I can count the elements in this subgroup. That's the basic fact, and I prove it in the notes, so let's do an example of this. So the first example is Z6 with a plus, right? And we had some interesting orders there. So order of 1 was 6, order of 2 was 3, and order of 3 was 2. And this should match up with a certain subgroup, which is generated by this guy. So the subgroup generated by 1 is the whole group, right? So it's 1, 2, 3, 4, 5, and 6, which is 0. And then it repeats. So these are 6 elements here, which corresponds to the order being 6. Now for the subgroup generated by 2, I take multiples of 2 in this group. So it's 2, 4, and 6, which is 0. So this is 1, 2, 3, order 3. And finally, subgroup generated by 3 is simply 3 and 6, which is 0. Yeah, it's 2. Right. Okay, and now we come to some of the most important definitions. So G inside G, which is again a finite group, is a generator if G coincides with the set of powers of this guy. And observation is, so G is a generator. Here comes something important. If and only if the order of this guy is equal to the order of the group. So we can explain this by, so indeed, we have this subgroup, and the order of this, so the number of elements in this subgroup, is equal to the order. And so we have one set inside the other, and these two are equal if and only if the cardinalities of them are equal. So if this is a generator, then they are equal and the orders are equal. Order of this is equal to the order of the group. And conversely, if these two orders are the same, it means that I have two sets of the same cardinality, so they are equal, and G is a generator. So let's look at elements which are generators and not generators. Okay, so let's look at Zn with a plus. So like one of those guys. It has generator 1. Just because by definition all those guys are like 1, 2, 3, 4, and they are all multiples. So that's nothing. They are all multiples of this, so it's a generator. Okay, now let's study some of those groups we're interested in, like Zp star. And then also we'll look at Z8 star. So what should we do? So let's take Z5 star. So basically what I want to do with this group, I want to look at various orders of elements, and I want to look at whether it has a generator or not. So the elements are 1, 2, 3, and 4. And let's list their orders. So order of 1, order of 2, order of 3. So here it's about taking powers to get neutral element E. Order of 1 is 1, that's always the case in multiplicative situation. Now order of 2. So I need to take 2 squared. That's 4, which is not equal to 1. Then I take 2 cubed, which is 2, also not equal to 1. But finally, 2 to the 4th is 16, it's equal to 1. Similarly here, I have 3 squared, which is 9, which is 4. 3 cubed will be 3, and 3 to the 4th will be 1. Order is 4, and 4 squared is minus 1 squared is 1. So order is 2. So we see that these are the orders, and 2 and 3 are generators. And 1 and 4 are not generators. Okay, so now we need some general fact from group theory to see how orders of the elements are related to the order of the group. And this is called Lagrange's theorem. Okay, so the following is true. So let G be a finite group. So if H is a subgroup, so I didn't define what a subgroup is. It's a subset which is stable under the operation. I explained this in the notes in some detail. If H is a subgroup, then order of H divides the order of G. So two integers and one must divide the other. It couldn't be like 13 and 2. Second, if G is an element, then order of this also divides the order of the group. And finally, for any element, if I take G to this power, I get neutral element. So there, it's some statement about divisibility of various things inside a finite group. Okay, so I put proof with quotation marks because it's not really a proof, because we don't prove one. So I prove only the easy bit. So this requires a bit more of group theory to make G act on a certain set to see that the group action will imply some kind of counting like this. But we prove the easier bits of how 1 implies 2. So if I take an element, I say let H be the subgroup spanned by this element, so set of powers like this. And then what happens is that the order of G, which is equal to the order of the subgroup it generates, will divide G by, here we use part 1. So I just look at a particular kind of subgroup and use 1. And this is the order. And also 2 implies 3. So we know that the order divides the order of the group, so I have something like this for a positive integer m. Because this divides this, so I can just divide one by the other. So then, yeah, I just need to see how this is the neutral element. But it's the usual Fermat's little theorem kind of argument. So I have G to this power or times m. And now I'm in the group, so the way to compute this, we can first take this and then take mth power. So this is the neutral element by definition of what the order is. And so this is just neutral element. As soon as I take any multiple of the order as the power, it's also the neutral element. Yeah, so there's some logical relations between the statements. And this one is slightly non-trivial, we're not proving it now. Okay, but now we have enough machinery to just prove Euler's theorem in one line. Let's do this. So proof of Euler's theorem. So first recall what the statement was. So we have been doing some more formal business, so maybe we've forgotten what the statement. So the statement is, recall the statement. So n is a positive integer, a is coprime to n, then taking this power gives me 1 mod n. And you see, in Zn star language, we can write the following statement. The statement is, so the same statement we write as follows. If I have A inside Zn star, then, so I can write the bar here, then what? Then this is 1, so A to phi of n is 1 in Zn star. So we work with elements which are invertible mod n. Okay, right, but this is true. So this is true by Lagrange's theorem. Because, right, so because what? So I have a group, Zn star is a group of order phi n. And one of the statements in Lagrange's theorem was that taking the order of the group as an exponent here will give a neutral element which is 1. Yeah? So the statement was that g to this power is the neutral element. And here is how it looks in this case. This is 1, this is phi of n, and this is a bar. Okay, so this is the proof. So okay, it's not quite one line, but it's morally nothing happens here. We just translate it into a different language and then apply a bigger result, and it's over. And another definition, which is this generators in this case. So an integer a, which is co-prime to n, is called, yeah, so here come primitive roots. Modulo n. If this element in this group is a generator. Right, so how does it relate to the orders? So I explained that an element is a generator, so this equivalently we can ask the order of this guy is equal to the order of the group. The order of the group is phi of n. So we are thinking about elements of maximal order. Yeah? Yeah, so informally, or actually quite formally, so these are elements. Okay, maybe let's put it in quotes, like elements of maximal order. Okay, let's do one more case study. So let's do Z7 star. So phi of 7 is 6. I have 6 elements, and then I can list orders of, yeah, so the question is this. So find orders of all elements and describe all primitive roots. So primitive root is just an old-fashioned terminology to say generator. So there's not much primitive or not much root about it, but it's just a generator in this context all primitive roots. That's kind of a standard question in this field. Yeah, so let's see what we do. So we list. So the important thing is first note that orders of all elements divide the order of the group. This is how it always goes. I'm looking at a certain group of certain order, then all elements will have orders dividing 6. This was part of Lagrange's theorem. Lagrange's theorem. Orders divide order of the group. So in practice, they can be 1, 2, 3, and 6. And among them, primitive roots will be of maximal order. Okay, so that seems quite a nice thing to compute. So let's list the elements 1, 2, 3, 4, 5, and 6. 6 elements. So this is the A bar. Now let's put the order of A bar, and here put some computations. Okay, order of 1 is 1. We can also try to look at simplest elements first. So 6 is minus 1. If I square it, I get a 1. That's order 2. Minus 1 has order 2. Now there are these other guys. Mod 7, right? So let's see. And also I need only to be checking these 4 powers. So order 1 is only the identity element, the neutral element, and so it could be 2, 3, or 6. So for example, here I should do 2 squared, and if it doesn't work, to the cube, and if it doesn't work, then it's order 6, it's done. So let's see. So 2 squared is 4. This is not 1, and 2 cubed is 8. It is a 1. So the order is 3. Now 3 squared. Ooh, it's a 9. Mod 7, it's a 2. This is not a 1, but 3 cubed is 27. 3 cubed is 27. It's a 6. This is also not a 1. So you see, this is some bits of logic. Then the order must be 6, because it's not 1, not 2, and not 3. But of course, if I wanted, I can do 2 to the 6, so sorry, 3 to the 6 and get a 1. So this is 6. Now 4 squared, 16, 2. 4 cubed, it's 2 times 4, 8, so 1, so order 3. 5 squared, 25. Mod 7. No. 25. Mod 7, it will be 21 plus 4, so it's 4. It's not a 1. 5 cubed. I can take this times 5, it's 20. It's 6. And you see again, order is 6 because it's not 2 and not 3. Okay, so we are finishing. Let's just mark the primitive roots. Maximal order, maximal order. These are primitive roots or generators. Are 3 and 5. Okay, so next time we'll prove that mod prime, there's always a primitive root. Okay, see you tomorrow.